Now we consider an example that has friction. So in this case, Alice needs to push a chair across a rough floor. The chair has a weight of 60 newtons, which is equivalent to a mass of 6 kilograms. When Alice pushes with a force of 10 newtons, the chair does not move. We want to determine how much static friction acts on the chair. We want to draw the direction of the frictional force. So one of the key things here is that the chair does not move. The fact that the chair does not move means that there is no acceleration, and that also means if there's no acceleration, that the net force has to be equal to zero. So in order for there to be a net force of zero, the frictional force is going to have to be opposite the direction of the push, which is always going to be the case in terms of the relative motion direction. So whatever direction the object would tend to move, the frictional force would be opposite to that direction in terms of the sliding surfaces. So we know that the net force has to be equal to zero. So as I look at the sum of the forces that are acting on my chair, I have a positive force along the horizontal direction that's acting to the right, that's the push. And then I have to add to it the frictional force, but the frictional force is acting in the opposite direction to the left, so it's negative. And so the sum of these forces added together have to be equal to zero because the chair does not move. So that means the frictional force has to be equal to zero, and we've drawn in that picture the direction of that frictional force. So now we consider a slightly different situation. So here, again, Alice needs to push this same chair across a rough surface. Chair has that same weight of 60 newtons. So in this case, when Alice pushes with a force of 40 newtons, the chair actually accelerates to the right. A kinetic frictional force of 30 newtons acts on the chair during the motion. We want to draw all the forces on the figure that applied force by Alice, the frictional force, force of gravity, and any support force. And then we want to determine the acceleration of the chair. After we do that, we also want to determine the coefficient of friction. So there's a lot of information in this particular example. So it's good to read it all the way through and then go back and start to put information in the figure. So we know that Alice is pushing with a force of 30 newtons to the right. We also know that there is a frictional force that is acting on the chair during the motion, and this is kinetic friction because the chair is in motion, and that frictional force is acting to the left, and it has a force of 30 newtons. So we can use the fact that the sum of the forces along the horizontal direction, there's a mistake here, this is not equal to zero, because we can't have 0 equal to 10, so just ignore that 0 there. So the sum of the forces have to be equal to the positive force that's acting to the right, which is 40 newtons, and then I have to add to it the frictional force, which is acting to the left, so that gives me a net force of 10 newtons. So again, it's not equal to 0. This was a copy and paste error. So the net force acting on this chair is going to be equal to 10 newtons. We can then determine the acceleration as we did before, the net force divided by the mass. The net force in this case is 10 newtons, the mass is 6 kilograms. So the acceleration of this chair will be 1.67 meters per second squared, and that frictional force will always stay the same because it's kinetic friction for this particular surface. The previous example, the static frictional force was dependent on how big of a push was being applied on the chair. So we can also draw in the other forces that we have. We have the weight of the chair acting down, and then we have this support force acting up. And we'd like to determine what that support force is so that we can determine the coefficient of friction between the chair surface and the ground surface here. And we know the coefficient of friction is just the frictional force divided by this normal force. So as we look at this picture, we realize that the chair is not moving in the vertical direction. So there is this support force acting up. And in this case, the sum of the forces along the vertical direction do have to equal 0. And so because it's not moving in the vertical direction, and so we have an upward force, which is the normal force acting up, and we have to add to it any other vertical force. And in this case, we have a force of gravity acting down, and therefore it's negative because it's acting downward. And so the sum of these, this is terrible, I made another mistake here. So this is not equal to 60, but the normal force in this case is equal to 60. So this has to equal 0, and the only way that this can equal 0 is if the normal force is equal to 60 newtons. This terrible cut and paste error. So once we know the frictional force that's acting and the normal force, we can determine the coefficient of friction, which tells us, how easy or hard it is to have these surfaces slide together. And so the frictional force acting is 30 newtons, and the normal force is 60. So the coefficient of friction is going to be 30 divided by 60, which is 0.5.